Okay.
Okay,
Then
so
we
there is no further questions from the audience. So we can take a break for 5 minutes, and after 5 minutes, I will restart the session.
okay.
I'm not sure whether I can start recording or what to do.
Yes.
There is
Well,
an
two things. I can already make you a host.
Yes, it is there already. In more buttons, there is a record option available. Record on this computer and record on cloud. So
what
what
I
are you?
sorry, I will pause.
Uh, Good afternoon, everyone. So we start with the next session of this particular GIAN course on fatigue of composite materials. You have gone through the. I hope I am audible to everyone. I hope I am audible to everyone. Can anyone confirm?
Yes, you are audible.
Okay, okay. So we start the session today, and this particular session is something to talk about the fatigue damage mechanisms briefly, and then I go on to talk about some basic ideas on fatigue for those who are new to this particular domain of fatigue testing and fatigue of metals and composites. I will touch upon what is the basic difference that you expect between the fatigue of metals and fatigue of composite materials as such. And then we go on to talk about some of the case study. One of the work that is the work of my PhD student regarding the fatigue of composite materials, where the matrix was derived from recycled PET, which is again a sustainability issue these days. And in that discussion, I will touch upon the various issues which were highlighted in the last four lectures on stiffness degradation or temperature rise during the fatigue testing, and on what we call as the hysteresis loop plots. What data can be inferred from the hysteresis loops, how stiffness degradation can be correlated from the hysteresis loops which we plot during the tests. And then we then go on in the last briefly about the statistical modeling of the fatigue life data using Weibull distribution, where we talk about something about the goodness of fit test also, which was referred to by the external expert briefly. So if I start my presentation today, all of us, again, I start with very basics of what we call as fatigue. What we understand is that all of us, mechanical or civil engineers, have a what we call as a perception that the material is homogeneous, isotropic, and mostly we'll talk about metallic materials earlier. And that is why now what we problem is that fiber reinforced materials or fiber reinforced composites, they are neither homogeneous nor isotropic, and that is why the difference in their behavior is also noticeable, and especially in terms of the fatigue failure. Initially, when people starting talking about fatigue of composites, so as we already know that the fatigue behavior of metals have been studied extensively, and people are aware about many theoretical, you can say, background is there. The experimental data is also immense. And the first instance, people tried to apply the same test methods, which some of them are valid, like modeling using Weibull distribution is valid, but there are the interpretation of the results need to be taken separately. But in the beginning, as the data was very less, so people started taking fatigue of composites similar to the fatigue of metals. So I will touch upon briefly that what is the difference that to expect in terms of the damage mechanism, and then we go forward. So, continuing with the same discussion, that when we study strength of materials as civil engineers or as mechanical engineers, what we understand is again idealized material, but simultaneously we also study and we know that the inherent flaws are always there in the structure. So these inherent flaws or defects that we call them as, they are actually the reason for most of the fatigue failures. and the presence of inherent flaws is too large in the probability of having flaws is too large in the case of composite materials, because they are actually multi-material systems, and that is why the fatigue of composites itself is very complex to talk about. This is just an idea. Professor Vassilopoulos also touched upon this. You have already seen this image of Aloha Airlines, where we find that the failure was there. I have just added one another image here, which highlights just for 10 seconds. I'll take that what is the importance of this study. So if you are looking into the history, you will find that the first commercial airliner was manufactured by the de Havilland Comet. It was not Boeing or Airbus. There is a confusion that why it failed. So there was a failure in 1954, and then people talked about this. And if you look at the bottom right corner, you find the basic reason were found to be stress concentration and then fatigue loading. One culprit which people found was that the aircraft had square windows. So that is why most of the aircraft these days do not have square windows. They have oval or circular, actually oval windows. So those of you who are familiar with the mechanical engineering, they understand the concept of stress razors, and that is why we find that the importance of a study of fatigue and fracture is there. That because we are working with the structures, they may be aircraft structures, they may be bridges, there may be other ones, which are very critical, and that is why we do not want them to fail, and that is what makes the study very important for us. So. We understand that if you go over the basic definition of fatigue, it says that there is an observation that when a material is subjected to dynamic, repetitive, or fluctuating load, they fail at a stress value which is much lower than that is required for a static test. That is the basic understanding that we had in case of fatigue. That means if a material has a ultimate strength of 100 megapascals, so if it is applied in static test is applied, static load is applied to it, it shall not fail below 100. But it is observed that when a repetitive load is applied, it fails at very much lower values. Those of you who belong to mechanical engineering or civil engineering even, we then coined a term known as the endurance limit. Typically, the endurance limit values, if anyone can suggest me, is approximately how much times the ultimate strength or the yield strength, if you talk about yielding. Typically, the endurance limit values can be related, for metals, they can be related to the yield strength of the metals. Any ideas what is the value that we normally use? It's
30%, sir.
Hello, I couldn't get what you said. Can you just repeat that?
So generally it's 30% of UTS, sir.
Yeah, there's a range 30, 40, 50. So for steel, we may use even 50% values there. That if the yield strength is 100, I expect that the endurance limit may be 40 or 50 megapascals. So that's the reason. But now this was an observation. Obviously, everything starts from an observation in science and engineering. So this was an observation. Based upon that observation, then people started working on it. That what is the reason for that? And that is why there was a study of the fatigue failure mechanisms. That why does this happen? Why a material which can sustain a load of 100 fails at a load of 50 when the same load is applied repetitively? And that is where the study of fatigue and then followed by fracture mechanics came into picture. If you take it very simply, that the factors which are necessary to cause fatigue failure is sufficiently high maximum tensile stress. We are talking about metal fatigue, large variation or fluctuation in stresses, and sufficiently large number of stress cycles. So if these three things are present, we may expect a fatigue failure to happen. And I caution you again, I am referring to metal fatigue in the beginning here. So if this is a typical diagram, if you find in many books here. What we have plotted is that we have plotted endurance limit versus the ultimate tensile strength. We are plotting the endurance limit versus the ultimate tensile strength. So if you look at the axis here, I can follow one line here, which is where we find that sigma E upon UTS is 1. means if the UTS is 1000, the ultimate the endurance limit is also 1000. So ideally, if there is no fatigue failure, we shall expect this. But we do not have that, and that is why now what we find is that typically you follow the lines that you are seeing here. You are following a line which is different here as the ratio is sigma E upon UTS as 0.5, and then you can have somebody said 0.3, that is also possible. And typically there is a band. If you what you see is the shaded area, that is a band in which most of the metals will lie. They'll perform in particular band, steel, aluminium, titanium, depending upon the type of metal, the ratio will be different. So that is why, but still you cannot reach here. And that is the basic reason why we find that it is important for us to study the mechanism behind fatigue. So, as I said, the reason was that we wanted to know that how does it happen? That if the stress is low, then how does that how the failure is possible? So, for metals, it is understood that, as I already said, that you do not have perfect materials, perfect structures. There may be deviations in the structures. There may be holes. There may be stress razors, and it is expected that in such case there will be what will cause as crack initiation and crack propagation. I will not go into the details here because we'll spend too much time on this particular aspect. But the crack initiation is what is talked about as the basic reason or the starting mechanism for metal fatigue. If you look at this diagram, which is the cross section of a metal specimen which has failed by fatigue failure, so we find that the process is followed: crack initiation, crack deepening, crack growth, and then leading to the failure. So we find that you initially, in the case of metals, you have a stress razor, and then the crack starts developing as you keep on loading the material again and again and again, specifically in tensile stress. So we understand that tensile stress will cause opening of the cracks. So that is what is happening. And then what you find is that if you magnify it further, we find that you find these circles here, which are typically called as striations. In metallurgy term and in metal fatigue term, these are called as striations, means they represent the growth of crack. So the crack is initiating, then it is growing, and then finally the failure happens. So the crack is initiating, the crack is propagating, and then the final fracture, if you find here, is a catastrophic failure. So there is a difference in this region. Those of you who are familiar with ductile and brittle fracture, they can very easily see that this is the typical way in which a material or a metal will fail, and we call this as a progressive damage mechanism. Progressive means the damage progresses. Initially, at 0 cycles, there may be a small damage, which is very, very small, not significant. As we keep on increasing the load, increasing the number of cycles, not load, we find that the damage is now accumulating. The sample is taking the damage. It keeps on accumulating the damage, and finally the failure takes place. So, and this is one more view of what you expect in metal fatigue. So actually the crack started somewhere here at the bottom part, starts flowing, growth, and then this is the final part, the crack propagation region, and this is the final fracture zone. This is typically what you expect in metal specimens which are failed by fatigue failure. So now I'll come to what happens in what we call as a composite fatigue in a moment. Before going there, let us touch upon some basics. We have already talked about this lately, but again I want to repeat that. So we have a fluctuating load, and we have now this diagram sums up what we have, the various terminologies that we are using in fatigue loading. Sigma maximum, the maximum stress. Sigma minimum is the minimum stress. Sigma amplitude, the mean stress, sigma m. So this mean stress is there. And this is the definition for alternating stress, or what we call as the sigma amplitude, max minus minimum by 2. And then the mean stress is max plus minimum by 2. In your rotating bending test, which is called as fully reversed bending, so your sigma maximum is plus 100 and sigma minimum is minus 100. So the mean value actually is 0 there. we'll see that. So then another important term which is used in fatigue testing is R, the stress ratio, which is actually a measure of the mean stress itself. We'll see how. So we understand R is nothing but the ratio of sigma minimum to sigma maximum. What is the ratio of sigma minimum to maximum? That is what we are calling it as R. And as I write here, that R is equal to -1 in the case of fully reversed bending. Fully reversed is just here. If you look at the top figure, this is the 0. This is the 0. So the maximum is maybe in tension plus 100, minus is in minus 100. So the ratio then happens to be R happens to be -1. Minimum is -100 upon 100. So you have R as -1. There are other values which are possible. So this is the definition of what we call as alternating stress. Mean stress already defined. This is a repetition, sorry. Now, so these are the different cases that we expect in the case of various stress ratios. So we start with the fully reversed bending. That is what we find here. R is equal to -1. Then is tension fatigue. That is typically the case in the case of most of the composite structures where the compression loading we are not going to test. We are taking, now the 0 is here at the bottom and the mean stress is not 0. The mean stress is here. Sigma m is having some positive value. And this is sigma maximum. Now the amplitude is applied onto the cycle is applied now on this mean stress. So the sample will always be subjected to this sigma m value, which was 0 here. And this is a definite tensile value here. This mean stress has a lot of effect on the fatigue life and the performance. And this also gives rise to what we yesterday may be talking about as the creep fatigue interaction, because there is some value of mean stress which is always there present in the sample. Then the next, so this is tension. The coming to tension compression fatigue is, now what we find is that the maximum value sigma max is positive, the minimum value is negative, and this is the 0 value. The mean stress is still positive. So in tension compression fatigue, you can have one case where the mean stress is still positive tensile, but the minimum value is what you call as the compressive stress. There is also a case of tension compression fatigue that you find here, in which the mean stress has now gone to negative value. That's my mean stress is compression, and then sigma maximum and sigma minimum. Sigma max is still tension, sigma minimum is compression. This kind of tests where we find, can say the R value correspondingly varies. Similarly, you can have compression fatigue, where the maximum and the minimum values both are in the compression side, and this is the 0 value, this is the minimum, the mean value. Or you can have one more typical case where we find that is only one directional stress. Means you are talking to sigma minimum is going to 0 now. So when sigma minimum goes to 0, R goes to 0. So these are the typical cases that we can expect here. Now, just to explain what is the importance of, what is the reason for understanding the effect of mean stress. So if you look at this diagram, we find that I've just plotted one curve here. That is the loading curve. And we are now taking, can anyone tell me what is the mean value, mean stress value here? In this particular case, this is the red line is the 0 line. What is the mean stress in this particular loading case?
0, 0.
Yeah, here the mean stress is 0. So we find here the sigma maximum is the sigma amplitude. You can find out here the maximum stress amplitude. That is typically what we find as in a SN diagram, the value of S. If you look at this tensile stress axis, we find that I have termed one blue dot here, which is the ultimate tensile strength, or actually I shall write it as ultimate tensile strength. So we find here. I request everyone to mute their microphones because somebody's microphone is on. So if you are at a mean stress 0, that is R is equal to -1, this is what is typically the case. And the reason why I have plotted a UTS here is that if you continue loading in one cycle only, follow this line, you expect that the material will fail beyond this particular blue point. After that, the material will fail. But if I continue with mean stress and subject it to sigma max as this value, I expect that the material will not fail. And if you recall our just discussion previously in metals, we said that the endurance limit, that is the maximum stress up to which there will be no fatigue failure, is approximately 0.5 of the 0.3 of the UTS. So somewhere here, if you see the amplitude is up to this point that I'm marking here, there will not be any failure at all. Let us see. So in this case, what do I expect right now? In this particular case, if this is the endurance limit that the pointer is at, do I expect any failure? If the endurance limit is at this point where the pointer I'm pointing, I do not expect any failure to take place because your stress values are much below that. The amplitude, the stress value is much below that. Let us take the next case. So there the average mean stress was 0. Now I change the mean stress value. Then I shift it to a positive value. So I shift it to a positive value. Now this is the value of the mean stress. It has some positive stress already always imposed on the specimen. And if I now put the same cycle of loading onto here, if I now look at it carefully, the sigma amplitude with reference to the mean stress is the same. The amplitude remains the same. The maximum value changes, but the amplitude as such, we are finding it is the same one that is there. The alternating stress value is same. So you find here now that if the mean stress is here, I am nearing the ultimate tensile strength, or I may have already crossed the endurance limit. If you further shift the mean stress up, and now here I apply the load, the same load, alternating load is applied on this value of the mean stress. What is expected now? Do I expect failure? Immediate failure. We expect immediate failures because although the amplitude is same, but the mean stress is too high. So this is the concept of what we call as stress ratio R, and the effect of mean stress. What will be the effect of the mean stress on the ascent diagram? That number of cycles and actually the amplitude of loading. And this is typically signified in this particular diagram. So this is a typical ascent diagram, which is where we are plotting sigma stress amplitude versus cycles to failure for 3 different values of mean stress, M1, M2, M3, where M3 is the largest mean stress. So in tension, actually, we are talking about the tension fatigue. So what we find here is that when you are increasing the value of the mean stress, sigma M3 is the largest mean stress, the fatigue performance is degrading. You can then take less stress can be withstood by the material if you want to take the same number of cycles. So that is the effect of what we call as mean stress. Same is shown here in terms of sigma m is equal to 0, the central one. This is sigma m in tension. So when you do that, just like increasing it, so it is lowered. Compression gives the opposite effect in metals specifically because that is crack closure. But the lower curve is not typically seen in the case of, not valid for composites, because here the compression will also play a different role of buckling, and it will also cause failures. Now, related to this is now what Professor was talking earlier, the concept of CLDs. And before going to CLDs, we have what we call as the failure diagrams. What we understand here is, again, we are plotting the mean stress versus the stress amplitude. And what is seen is that you have 0 here. The stress amplitude increases this way. And if this is the yield strength, this is the endurance limit. Similarly, this is the yield strength, and this is the endurance limit. So if you talk about no stress amplitude at all, we find that the material will fail here at yielding, or if you take ultimate failure, it will fail here. But in between, what you have is the various yield criteria. We have the Soderberg line, the Goodman line, and the Gerber parabola. It's not a line, actually, it shall be parabola here. And this is the basic reasoning for drawing the CLDs. That is where the CLDs come from, what we call as constant life diagrams. Now, so typically, when I talk about fatigue now specifically for metals as well as for composites. I like the second line, which is by a very famous author in fatigue, Professor Ramesh Talreja. Those of you who work on fatigue know he's a very old professor. He's an Indian, a person of Indian origin. He suggested this line, and I have picked it from here, that the fatigue damage is happening because of irreversibility. The material behavior is irreversible, and summed up in the second line, that what in the material state is different when the load was applied for the first time is reduced to zero. So you start from zero, apply a load the first cycle, and then come back to zero. That means the red line is you have taken one cycle loading compared to when the load was zero for the first time. So zero for the first time is initially. That is, so there is a difference between the first at what is at the end of the first cycle, although the load is zero, but you have taken one cycle of loading. So there is something which has happened, which we say is nothing but damage accumulation. So damage is accumulating, and I pick up this very simple figure from Talreja, where we find that this is the virgin material. As you keep on increasing the number of cycles, we find that something is happening. The damage is growing. That means the material is accumulating damage. And that is where, as I said, I like this particular line by Talreja, where he said that there is something difference in the material when the load is reduced from to zero after the first cycle, then when I compare it to when it was zero for the first time. So there is this, the behavior is what we call as the damage development or damage accumulation, which is responsible for fatigue failure. I'll skip this slide and go nextly. So the basic difference now, that what is the difference between fatigue phenomena in metals and composites is that unlike metals, composite materials, as we say, are inhomogeneous and anisotropic. And then another difference, they start accumulating damage in a general fashion rather than a localized fashion. Localized means in our previous slide, we have seen that there was one crack which was propagating, and that particular crack after propagation has caused fatigue failure in a metal. The same thing is not true for composite materials, because you have multiple sites. There are multiple sites, multiple damage mechanisms which start taking what we call as load, and then there is not a single macroscopic crack which will be responsible for the failure of that particular material system. There is a combination of failure of many particular systems which is causing this failure in the case of composite materials, and that is what is making it more complex to study. So that's what we write here, that microstructural mechanisms of damage, which may be different ones like fiber breakage, matrix cracking, debonding, transverse ply cracking, delamination, they all are there responsible for the failure of a composite material in fatigue. This is one example of different damage modes. You can have delamination. For those of you who are new to composite materials, this is called delamination because you have different laminates which are put together. You may have debonding in between the matrix and the fiber. The fiber breakage may be there, pull out may be there. And then this is typical bridging concept, which is in many ways helpful in increasing the fatigue life, similar to what happens at the crack tip plastic zone in the case of metals, where it helps us further in increasing the fatigue life. So this is one more one picture which we take from a very old source, where we find that matrix cracking is originating. These are all optical normal images. We find that initially at maybe only at 10,000 cycles, no matrix cracks, and then we find further it is growing, just to tell us that what I said in my previous slide, that in composite materials, what we find is that the damage is not a very specific point. It is at many sites at which the damage is happening. So this is something to tell the same thing about this, that there are various ways in which the damage can be there. One figure of which I like from again Talreja, a very old text, is where they show the crack bridging, where we find that the crack bridging is clearly visible in this particular image. Very typically used in my lectures on composite material fatigue for normally PG students, where it is very easy to visualize what is there. So these are, and then we said that there are defects And the composite materials are more prone to defects because of the nature of manufacturing methods, because they are not manufactured by the traditional manufacturing methods that are used for metals. So they have a typical, can say, methods which are there, which cause many kind of manufacturing defects, which are further acting as stress raisers, and then they start the fatigue failure, or the damage accumulation starts at those points again. We just talked about the stiffness loss in our previous, the professor talked about in the previous slide itself, and he'll further take away this discussion in his next class about stiffness degradation. So what is observed is that the stiffness degradation is observed when you increase the number of cycles. So you start with 0 number of cycles, the stiffness is normalized value is 1, and as you go forward, we find that the residual stiffness, the stiffness, residual means the remaining stiffness of the sample is there. Residual stiffness is somewhat easy to measure. So residual strength is a tough one. You need to break the sample, but we will see how residual stiffness can be measured experimentally in our next slides. So after going through this basic aspect of composite material fatigue and something general observations about the fatigue itself, we now take up one material system where the aim was to study the fatigue behavior of composite materials which are using recycled PET as a matrix material. So PET is polyethylene terephthalate, which is the typical polymer used for making your Coke and other cold drink bottles, water bottles, consumed in very large quantities and then thrown away after usage. So it is a very big challenge to the sustainability. In India, most of it is recycled. Recycled in various ways, chemically and mechanically. This project aimed to take out PET from market, the waste PET, and recycle it chemically to generate what we call as a thermosetting polyester resin out of that. And that resin was used as a matrix material for making composite materials, using glass fiber as a reinforcement. So we then compared the performance of fatigue performance of this particular composite material with the one which is using virgin polyester resin. Although it is expected, and on the expected lines, the performance of the recycled resin is lower than the virgin resins. And then the next part of the project was to bring the value of fatigue performance of this recycled resin almost at par with the virgin material by addition of some other supplementary materials, which we call as, in this particular case, the graphene nanoplatelets were used. So, if you are interested to read something about the recycled PET, this is one very good paper, a review paper, again from the same student, which is summing up almost all the activities until the 2021, almost 3-year-old now, where we sum up that the usage of recycled PET as a matrix material in composite materials. So it's a very comprehensive review which the users can download if they are interested in studying further on it. So what we did is that we extracted the resin from the waste PET, and then this is a typical diagram through which in the lab setup, basically a small reactor through which we extracted polyester resin from the PET flakes which are available in market, and then the characterization of that is done, and then further using that particular resin. The next discussion that we have is from this particular paper on fatigue performance of RPET composites. The next stage is now to make a composite sample that we are testing in our fatigue test. So as we have discussed earlier yesterday, that there are ASTM standards which specify the standard some typical dimensions. So in this particular setup, we have used vacuum infusion process for making these sheets, out of which the samples have been cut through diamond saw. So this is again a laboratory setup in which the vacuum infusion process was used for making samples, and below is the two types of samples which are manufactured using this particular setup. The fiber, and then coming to the test setup, which we'll show tomorrow also. This is the basic MTS 250 CAN setup, which we are using. On the left side is the basic machine. In this particular project, what we have done is that we have measured the damage evolution using transmission light for photography, using a light source at the back of the sample and using a digital camera. And simultaneously, what we have used is the damage evolution has also been studied using the temperature measurement of the surface of the sample using a IR type of image analyzer along with a IR camera. So that software along with the hardware has helped us to find out the temperature rise that goes on during the cycling of the sample. If you come to the results here, as we expected, and this is the typical Baskin equation, which was discussed maybe day before yesterday's also, which is still used, very old equation, but still used for typically signifying the SN curve for in the SN curve studies. So what we observe is that the red line is our material that we tested in the lab, and the black one is from a reference paper by Vassilopoulos, a very old one. I remember, I think it's in 2008 or 9 somewhere they published this paper. We have used the same fiber reinforcement, the same stacking sequence and the same type of fibers have been used, glass fibers, just to compare our results with the experimental, with the results available in the literature. So what we observe is that the typical recycled resin, the SN curve is much lower. The fatigue performance is quite low as compared to the virgin material, which we expected also. The next thing that we did is now we then went on to study the evolution of. Then the next thing that we did is that we went on to study the evolution of hysteresis loops. So what we find here is if you look at just one of the diagrams, which is at around for particular S value of 80%, or if you talk about anyone, let's say 45%, we find here that what we see here is that we are now plotting the sigma maximum upon UTS normalized value versus at these typical 5 loops. If you see, they are at 0%, means the first cycle of fatigue loading. Then near to the failure, almost 100%. In between, 25% and 75%. What is observed is that there are 2 observations. Can anyone tell me that what do we observe in any of these figures? What is happening to the hysteresis loops? The black one is the first cycle of loading. The purple one is maybe the last cycle of loading. Your voice is not audible. You need to unmute yourself. So what I'm not, yeah. Hello. So what we observe, you're trying to speak, but I'm not able to hear properly. Anyway, so yeah, what we observe rightly is that one thing is that the slope of the curve is the slope of the loops is changing. And if you go to basic science, it tells me the slope of the curve is a measure of stiffness. So we find what we just said, that stiffness degradation is happening. And it is possible to find out stiffness degradation qualitatively to the extent using the slope of these hysteresis loops. And another thing that we find here is the area of the loops. If you find the area of the loops is also increasing. If you look at the last diagram from this black one, which is very thin, we have come to a very large area. The area of the hysteresis loop is also an important parameter. So we find out both the things in this study. We study the slope of the hysteresis loops as well as we study the area of the loops, which is a measure of the damage accumulation in the material. And then what we observe simultaneously here, if you go to the next figure, is just the basic idea what is here. That if you start with the first one, we have the 2 issues. One is actually 3 issues here. One is the slope. The blue and the black one, they vary in slope. Second is the area. The blue one has a small area. The black one has a large area. The third is shifting of the loop. So there is cyclic strain. So somebody yesterday was asking about where do we observe creep? So this is one reason. One of the reasons of this shifting is the creep interaction coming into picture here, because we are testing at a particular sigma mean value. If you study at different mean values, you may find that this contribution of this may be different. We didn't do that, but it is possible to do that also. So the slope, as we said, is the stiffness measurement, slope is used for stiffness measurement, and then we have used the area for damage accumulation. And what we observe here is now that we are now seeing that the fatigue stiffness, how it is varying. So with this normalized stiffness, En to E1, and then plotted versus normalized number of cycles, where normalized means the maximum is obviously 1, the failure is there. If you do not normalize it, the answer, the plot will be not conveying anything, because at different stress values, the N value, absolute value will be different, and no information will be gathered out of that. And we find here that this is how the stiffness is degrading based upon the data that we collect from the hysteresis loop data here. The stiffness degradation is observed, and this is typical to what is observed in almost many of the composite systems. That we find that it is following a three-part curve. So initially the primary one is here, then you have almost the flat one, and the last one is here, which is actually talking about a very large the reduction in the stiffness, where the failure is very near. So this is one observation of stiffness degradation which is there. Then similarly, we talk about the area of the hysteresis loops also. So you can, as we said, that the area enclosed the hysteresis loop is referred to as an inelastic strain energy, and which also denotes dissipation in energy. So this is a representation of that something is happening in the material or damage is accumulating. So we are using the area increase in the hysteresis loops. We find again that there is a steady increase in the area, and then it increases rapidly once the failure is nearing. Now, the results from the optical observation that we find here is now from your transmission light observation. So you have put a light behind the sample. So glass fiber composites are typically translucent. So the light is normally transmitted. So you start with 0, means the sample which is fresh, there is no load onto it. As we keep on increasing the load, we find that the damage is seen, although it is a very, very qualitative and a very, very primitive method of measuring, because if you have multi-layers, we are still not able to see that in which layer the damage is happening. But on a large, on a gross scale, it is possible for us to observe these damages. And we find here that this is for two values. One of them, the upper one is for a high stress value. S here refers to the ratio of stress amplitude to the ultimate tensile strength, and S is 0.45. Again, the lower one is there. So we find here that again, this is 0%, 30%, 60% of the fatigue life, 80%, almost 90%. We were not able to capture very near to the failure because the sample fails, can say, catastrophically. It doesn't give us time for imaging. So that is why we find that damage is percolating into the sample, and it is observed normally with the help of a very simple setup also. Similarly, from the temperature data that we have here, now we are comparing here the temperature data for can say we find here that the fatigue damage also increases the self-generated temperature. So we find that if this is the data available to us for two stress levels, this is the initial sample, the blue one, it is very cold, and then when you keep on cycling, the temperature rises. The typical temperature that you get is with a lab temperature of 24. The maximum surface temperature was observed around 45 degrees, or nearly, not always less than 50 degrees actually. So this is for two stress levels. At higher stress levels, obviously we find there is too much redness, the temperature rise is too high here. And then here, at lower stress levels, the temperature rise is not that high. This is the temperature generation value, the approximate value that we find approximately, as we said, 45 to 48 degrees is the temperature rise that is observed at the surface of the specimen. Again, there are questions from literature that it is only measuring the surface temperature, not telling us about what is happening deep inside the material. That's right, but this again one way to qualify for some damage data there. This is the actual image of now the samples which are failed, telling us something about the damage process, that what kind of damage is observed in these type of samples. The typical samples which are failed, these are simple images of this plain photography, and then using a using an SEM to try to image something better. But the SEM images don't give us much of a much of a qualitative data or even a quantitative data. They are only representative data that we get from SEM imaging. You will only come to know that what is happening on a very, very gross scale. Okay, then that was for typical material which was recycled. Then we created what we call as a graphene modified composite, which is written here as RPT2. And when we observed that the black one was for our recycled PET without graphene, the the blue one is where the virgin one is from the literature, and the red one is now after modification. So we come very near to what we call as the fatigue performance of the virgin polyester resin. So that was one of the objectives of the project, was to improve upon the fatigue performance of your recycled resin-based material systems on comparable with the virgin-based system. So this is somewhat now comparable. It is very near to now what we call as the virgin material. And then here we are comparing now for two set of materials. PET1, GFR, RPET1 is without graphene, RPET2 is with graphene. And we find here that again is a stiffness degradation curve. If I look at this curve, it tells me that if I take N10 as the number of fatigue cycles which are at which 10% stiffness loss is observed, we find that this 10% from 1, if I come to 0.9, so if this is 1 normalized, if I come to 0.9, so the first three, one see that they come very fast, whereas for the other, the modified one, which is the graphene addition, we find that this 10% loss is observed at much higher values, 5.6 times, 10 times, or 9 times. So your fatigue damage is delayed. This is one reason for it. There are multiple reasons, again, probable reasons. We were not even experimentally, we can only probably say that this has happened because of fiber bridging, this has happened because of some other reasons, but we cannot certainly say that it is because of only this particular reason. That is one limitation with experimentation, that any experimentation that do, that you can only point to some probable reasons for that particular one. So we have the improvement in the stiffness degradation data. The stiffness degradation is delayed, which is giving us improved fatigue performance. Similarly, this is again the damage development. Although when you add graphene here, we are not able to see very clearly. It doesn't convey much of the data for our reference because the translucency of the specimen is somewhat lost. So you do not get that much clear picture because the sample becomes not a translucent one, almost a very opaque sample is there. So but still some typical data is observed. But here we find that the temperature data now supplements what the observation is. So the observation is that the fatigue performance is better. Why it is better? One thing I can say is that when I compare the top figure, which is for without modification RPT1, at the same stress levels of say 0.8, 0.8 here, the temperature rise in the modified one is very less in both the cases. So this is one reason. Again, an observation that telling me that the damage accumulation is less, and that is why the fatigue performance of the modified system has been improved than the unmodified system. This is again a simple imaging which is telling us something about that what is inside the system. Just again an observation one, not only for an observation, not much conclusions can be drawn out of these images. Then we go to the statistical analysis as we were referring to time and again the Weibull distribution. So we have then analyzed this data using two parameter Weibull distribution. For doing that, we need to put the data in a particular slot in a ascending order here. And in the morning session, somebody was asking about the statistical significance. If you look at this data set for 0.8, RPT1 stress level 0.8, we have the first sample failing at 520. The seventh one, we tested 7 samples, the last one at 4,450. So there are statistical methods available, like here we used an outlier criteria called as a Chauvenet outlet criteria, which tells me that this 520 does not belong to this population. Similarly, this is on a lower side. Similarly, you can have that if you get 4,450 and the eighth one is maybe 50,000, that is also insignificant. That means it doesn't belong to that population. So we are able to find out those outliers. like they are marked here with a hash here. This is outlier in this sample. This is the outlier. So these outliers are then removed or filtered before carrying out the statistical analysis, so that the statistical analysis is right and doesn't convey a wrong meaning. So we do that here, and then what we find is that after removing this data, we can then go for finding out. Now, this is a typical value of CDF and PDF for equation for the Weibull two-parameter Weibull distribution, where you have two parameters actually. The two parameters are alpha, and one of them, alpha is the shape parameter and u is the scale parameter. Typically, alpha specifies the spread in the data. Spread in the data. If you look at the alpha value here, you can see there are some numerical values 2.2, 1.9, and then for PET2 is 1.3, 1.6. Alpha signifies what is the spread in data. The higher is the spread, the lower will be the value of alpha. You will be reaching towards 1. You will be reaching towards 1. The lesser is the spread, higher will be the value of alpha. Like for a comparison, if you go for metal fatigue, this alpha value can be as high as 15, 16, 20 also. Whereas for typically a glass fiber polymer, we find the alpha values are 2.2, 1.9. You can, means alpha is actually reverse of spread. Lower value means more spread. So what is the observation? We have used different methods, the graphical method, the method of movements, the MLE estimator for finding out the values. And it tells me that the alpha values for the modified composites are lower, means the spread has gone from good to maybe not a that good one, because we have added one more element. We have added some particles into it which increase the heterogeneity, which may be responsible for increasing this spread itself. So this is an observation that we have improved the fatigue performance, but then it has a effect on the spread. The spread is more. So if the spread is given to us more, you can then use this alpha value to use to find out what we call as the design allowables, which further help us in going for designing of against fatigue failure of any kind of a material system. Similarly, we talked about the goodness of fit tests in the morning session. So we used a Kolmogorov-Smirnov goodness of fit test to tell that whether the data is belonging to the Weibull distribution or it is not belonging to the Weibull distribution. So the data or this particular goodness of fit test tells us that the data is belonging to the Weibull distribution. And our hypothesis, we started with the hypothesis and we have proved it right that okay, this data belongs to the spread can be modeled using the Weibull distribution. So we have tried to, I think we already are running on time now. We are 5 minutes over than 4 o'clock. So I'll try to sum up here that fatigue damage or fatigue behavior of fiber composites is quite different from that we observe in the case of metals. The basic terminology remains the same, but the damage modes are different. Damage modes are completely different, and that is why they need a total review of what we study for metal fatigue. Weibull distribution can be used for both the cases, but obviously the scale and the shape parameters will vary. The shape parameter typically will be varying too much for when I compare for metal fatigue and for composite fatigue. And this is as I said, a measure of spread. Again, there are formulations, there are observations from the data that scale parameter also depends upon the shape parameter. Sorry, also depends upon the stress value. At stress level at which you are testing, normally large spread is observed at lower stress values, whereas the spread goes to a lesser value when you increase the stress value. So these are the typical takeaways from this particular topic on fatigue of what we call as the composite material. So I will stop it here. If you have any questions, you can ask. Any questions about the experimental setup or the way it has been done? You can ask or you can email us. We will be happy to share the details, and we'll see the same setup in our tutorial lab session tomorrow, where we'll be demonstrating one of the fatigue tests for, again, the similar sample is available with us today. Yeah.
Raman,
Yeah.
I don't have a question. I just, while listening to your slides, following your presentation, I went back to Google and
Okay.
I recovered this. Probably you see my screen.
Yes, this is your this is your paper.
No, it's not my paper. This is from the Sandia, the Department of Energy of the United States.
Okay.
A lot of tests on, so this is page 96. Let me go to the top to show which one is it. So it's this one. So the analysis of the database.
Wind turbine blades. Yeah.
Yes, for wind turbine rotor blades, the Department of Energy. And I
Okay.
went back to this page 96, and here they have results
Okay.
of tension. So here on the top you see R equals 0, so tension,
Yeah.
fatigue. On the right hand you have R equal 10, so tension, compression.
Compression.
Exactly, and here down there on the right, there is the result from reverse loading, -1.
-1.
And
Okay.
this is to verify what you said during your presentation about the loops and the shift because of the creep. We see creep at 0.1.
Yes. Yeah.
Creep at
That's right. Yes, that's right.
there's no creep. There's no creep at -1
Yes.
because here
There
is
is no creep at -1. Yeah.
exactly.
That's right. That's what probably I was trying to say. And the people who are working in the domain, they will get what you, and they'll be more clear from this particular image. So thank you for helping me out.
Only
with
for
this.
supporting your work.
Yes.
It's a very nice and easy example that.
Yes. Yeah. So